So this is those are different exercises, 1, 2, 3, and 4, 3, 4, 5. They are exercises, questions. So I don't mean that we are going to have the same questions or the same exercises on the final exam, but it will be something like this. Okay, so first, explain the difference between sensible and latent heat. Well, I'm not going to answer this, but remember that we have been talking about this, and this is we spoke about this before the midterm. Okay, so I want you to understand that the final is going to be a comprehensive exam, so things included on the first lessons will be included on the exam. Okay, so the difference between sensible and latent heat, this is not after the midterm, this is before the midterm. It has to be with ventilation loads. So you have to go over that lesson and you have to write here the difference. Sebastian, okay, so we didn't go over your, I'll be with you in a minute when we are done with this. Okay, Sebastian?
All right.
Then rank the following material according to the thermal conductivity. Okay, so what do you think is the best material in terms of thermal conductivity? Which material is the number one? What do you think?
Polyester.
Polystyrene, yes. So this is why? Because it has the lowest thermal conductivity. I think I have explained this many times. And what is the second best?
Fiberboard?
Fiberboard? Yes, because here we have two thermal insulation materials. We have polystyrene and fiberboard. Wood, it's not considered a thermal insulating materials, and brick is not thermal insulating at all. Okay, so wood would be the third one, and brick would be the fourth. Okay, polystyrene and fiberboard are two thermal insulating materials. Polystyrene it has always the lowest thermal conductivity, so that's why it's the best. But between fiberboard and wood, there is a huge difference because this is a thermal insulating material and wood is not. And then between wood and brick, there is always a difference, and wood is better than brick. If you don't believe me, you can go over the Excel file. Especially, yeah, so on this Excel file, you remember that we have here the thermal conductivity, and we can go over this. We are looking at this value, the thermal conductivity. So the lowest, the lowest value would be the best. Okay, so wood, it's around 0.9, and fiberboard, fiber insulating board is 0.2. Okay, so wood is 0.9, and this is 0.2, so this is better. And then brick, it's 9. Okay, so brick is the worst, and polystyrene, it's 0.1. This is the best. Okay, so we have to memorize this. So well, memorize. I don't have to memorize this 0.17, but if I look at these materials, I don't have to check a table. I know that polystyrene is the best, fiberboard is the second best, then wood, and then brick. Okay, so then calculate the wet bulb temperature. Dry bulb temperature is this. Remember that you will have to use your ID number. So X is the final, I think it's written here, is the final figure, and Y is the second last figure of your ID. So what do we have to do? We have to work with this psychrometric Freedom Lab psychrometric chart. Remember that first we have to work with the settings because by default we have international units, so we need English, and then reset and submit. And now if we type 85 and 50, let's say. So this is 85, this is 50. Remember that we need this input data for our properties, submit. And the wet bulb temperature is 70.7. Okay.
Just a note, it says web bulb instead of wet.
Oh, thank you, wet bulb. Yeah, this is the wet bulb temperature. Okay, this is wet. I will save it. Thank you for letting me know. Then the solar power. Okay, so here it's about energy and power. The solar power on a surface of this is for 10 hours. How much energy is received? So here, if we are talking about, this is the power is a solar irradiance. So we have to turn power into energy. So let's do it. This is 90.6 BTU hour and feet square. Then we have to multiply times the area, 120 feet square. And then we have to multiply this times 10 hours. So that would be, well, whatever, 90.6 times 120 times 10, and units are important, okay? So you can make it, but if we are talking about energy, units are BTUs. Don't forget that. And then what is the amount of solar energy collected? Okay, so now we have the energy. What is the average solar power received over this period in 12 hours? And now we have to divide. So it's 1,400 kilowatt hours divided by we don't have information about the area, so we only have the 12 hours. So this is 12 hours. So whatever it is this, so 1,400 divided by 12, the units are kilowatts. Okay, so what is the average solar power? Okay, power, it's in kilowatts. And then if we want to, it's not specified here, but if we multiply this times 1,000, then we have watts. Here, what calculate the percentage of demand covered by the PV array? We are in Keene. The electrical energy demand in January is this. The maximum power of each panel is, well, here you have to calculate this with your ID, let's say 220. And we have 20 panels. And you know that we have with this, it's not specified, but we need to calculate the PV watts, or we need to use the PV watt software. So this is PV watts. Okay, so first we're in Keene, New Hampshire. Then there are 20 panels. Times the maximum power of each panel is, let's say, 200. No, 200, yes. So this is 4,000 watts. So the size of the DC size would be 4 kilowatts. Okay, so by default, we have 4 kilowatts, fine. And then the south orientation, if it's south, the azimuth is 180, and the angle of PV panels, it's, let's say it's 20. Okay, so by default, it's 20. So if you click here, we are in January. Okay, so we have the electrical energy demand in January. So we have the AC production in January. It is 312 kilowatt hour. So what is the percentage now? The percentage is covered by the PV array. When we have to calculate the percentage, it's always the same. We have to multiply 100 times the production, 312, divided by the total, it's 2,000. Okay, so this percentage would be 312 divided by 2,000 times 100. So this is 15.6%. Okay. So that's it. Here we have to make sure that we are comparing, because you can say, oh, we are producing 5,000. Yeah, we are producing 5,000 per year. But here we have the electric demand in January. Okay, so we have to compare January and January. So this is 15%. And then calculate the electrical heating load. We are in Keene. The heating load is 50,000 BTU hours. And okay, so here first we have the we have to turn this into watts. Okay, so we have 50,000 BTU hour. And now we have to divide this by 3.4121, whatever, watts per BTU hour. Watts per BTU hour. Divide or multiply? Well, we can always. BTU hour to watt. Okay, so if we are looking about 50,000, convert, this is 14. Okay. Yeah, so it's 5,000 divided, let me check this, 5,000, 50,000 divided by 3.4121. Yeah. Okay, this is 14,653 watts. Now we have to turn this into kilowatts. So it would be 14.6 kilowatts. Now, calculate the electric energy demand in January. So we have the heating load times 24 hours times 31 days. Here we divide this by 1,000. Well, I will delete this because we have already turned this into kilowatts. Okay, so let's do it. This is 14.6 kilowatts times how many hours? 24 hours per day times 31 days. So this is 14.6 times 24 times 31. This is 10,000, 10,862 kilowatt hours. Okay, so this is the demand. And now we have to compare this to the production. Well, we have to calculate the amount of PV panels to cover 100% of this electrical demand. So our AC production should be at least 10,862. And we have these panels, 200 watts per panel. And we have the south orientation, and the angle of panels is 30. Okay, so let's go back to PV watts. We are in Keene, New Hampshire. And now what they are asking for, we have to calculate the DC system size. We know that the angle is 30. The azimuth is 180 because it's south. Is it south? Yeah, south orientation. The angle of PV panels, or the tilt, is 30. And the maximum power of each panel is 200. Okay, so now we have to try. We can start trying with 4 to see what the the AC production is. So the AC energy is 5. No, sorry, it's because we are working with January. Yeah. Okay, so we have to produce 10,000 kilowatt hours in January. So 4, it's nothing. So let's make it with 40. Okay, with 40, here we are with 3,000, but it has to be 10,000. So we have to multiply this times 3. So probably this is 120. Okay, so now it's 10,600, and this is 10,800. So we need a little bit more, let's say 121. Okay, change it. 121. $122. Okay, so now it's 10,800. So that means that the DC size is 122 kilowatts. And this is 122,000 watts. Okay, so this is the DC size. If one panel is 200 watts, we divide this by 200 watts. So the number of panels is 122,000 divided by 200, 610. Okay, so first we have to approach the DC size so that the AC production is the same as the demand. And then we have to turn the DC size into watts, divide by the maximum power of one panel, and then we have the number of panels that we need.